Asymptotic notation lets us talk about how a function grows when the input size n becomes very large, ignoring lower-order terms and constant factors. Big O, f of n equals O of g of n means there exist positive constants c and n0 such that 0 less than or equal to f of n less than or equal to c times g of n for every n greater than or equal to n0. In plain English, f never grows faster than a constant multiple of g. Example: the running time of linear search is at most c times n, so it is O of n. Big omega, f of n equals omega of g of n if there are c greater than 0 and n0, so that f of n is greater than or equal to c times g of n for all n greater than or equal to n0. It is a lower bound. The algorithm will take at least this much time. Big theta, f of n equals theta of g of n when it is both O of g of n and omega of g of n. The growth rates match up to constant factors. Little o, f of n equals O of g of n if for every c greater than 0 there exists n0 such that f of n is less than c times g of n for n greater than or equal to n0. Equivalently, the limit as n approaches infinity of f of n divided by g of n equals 0. It is a strict upper bound. Little omega, f of n equals omega of g of n when the limit as n approaches infinity of f of n divided by g of n equals infinity. That is, f grows strictly faster than g. Property 1, reflexivity, f equals O of f. Property 2, transitivity. If f equals O of g and g equals O of h, then f equals O of h. Property 3, additivity. O of g sub 1 plus O of g sub 2 equals O of the maximum of g sub 1 and g sub 2. Property 4, multiplication by constants does not change the class. Analogy, think of O, omega, theta as speed limits on a highway. O is the maximum speed you are allowed to exceed, omega is the minimum speed you must maintain, and theta means you are stuck in a speed range that is neither too slow nor too fast, just the right speed corridor. Little o and little omega are like strictly below or strictly above that corridor. When we analyze an algorithm, we can look at 3 different scenarios. Best case, the smallest amount of work the algorithm could ever do. Example, searching for a value in an unsorted array. If the target is at index 0, the loop stops after one comparison, so the best case time is theta 1. Worst case, the most work the algorithm could possibly need. The same linear search, if the element is not present, must examine all n entries, giving theta. Average case, the expected work assuming a probability distribution over all possible inputs. To compute it, we define a random variable x that measures the cost for a given input. Then find expected value of x equals sigma cost of I times probability of I. Probability model. The model must be realistic. A common one for linear search is the uniform model where the target is equally likely to be in any of the n positions or absent. Under this model, the average number of comparisons is n plus 1 over 2, so the expected time is theta. Why the 3 matter? In some situations, for example quicksort, the worst case is rare but catastrophic. The average case gives a more practical picture. In real life, think of a cashier line. Best case is an empty line, worst case is a line of 100 people. Average case is the typical length you see throughout the day, which you can estimate from historical data. Many algorithms break a problem into smaller sub-problems. The total work can be expressed as a recurrence relation. 3 standard techniques to solve them are: master theorem works for recurrences of the form t of n equals a times t of n divided by b plus f of n, where a greater than or equal to 1, b greater than 1. Define c equals log base b of a then. If f of n equals big O of n to the c minus epsilon for some epsilon greater than 0, then t of n equals big theta of n to the c case 1. If f of n equals big theta of n to the c times log to the k of n for k greater than or equal to 0, then t of n equals big theta of n to the c times log to the k plus 1 of n case 2. If f of n equals big omega of n to the c plus epsilon, and a times f of n divided by b is less than or equal to k times f of n for some k less than 1, then t of n equals big theta of f of n case 3. Example, merge sort has a equals 2, b equals 2, f of n equals big theta of nc equals log base 2 of 2 equals 1, and f of n equals big theta of n to the c, so we are in case 2 with k equals 0. Therefore, t of n equals big theta of n log n. Recursion tree method, draw the recurrence as a tree where each node's cost is f at that subproblem size. Sum the costs level by level. For the merge sort tree, each level costs big theta of n and there are log base 2 of n levels, giving big theta of n log, and this visual method helps verify the master theorem or handle recurrences that do not fit it. Substitution induction method. Guess a bound often using the master theorem and prove it by mathematical induction. Example for binary search. Guess t of n less than or equal to c log n base case n equals 1 holds. And assuming it holds for n divided by 2, we have t of n equals t of n divided by 2 plus big O of 1 less than or equal to c log of n divided by 2 plus d equals c log n minus c log 2 plus d. Choose c greater than or equal to d divided by log 2 to finish the induction. Explanation. The cost of basic operations depends heavily on the data structure used. Below is a quick reference of common structures assuming n elements are stored. Array contiguous block of memory. Access by index, theta of 1 just compute address. Insertion/deletion at the end, theta of 1 amortized if we have capacity. Insertion at arbitrary position, theta of n because elements must be shifted. Analogy, a bookshelf where you can quickly grab a book at a known slot, but adding a book in the middle forces you to move all later books. Singly linked list nodes with a pointer to the next node. Search for a value, theta of n insertion at head, theta of 1, insertion after a known node, theta of 1. Access by index, theta of n must walk. Think of a train where you can add a carriage at the front instantly, but you have to travel through carriages to reach a specific one. Binary search tree balanced, e.g. a VL or red-black, each node has less than or equal to 2 children, height approximately log n search insert delete. Theta of log n traversal in order. Theta of n if the tree becomes unbalanced, worst case degrades to theta of n analogy. A well-organized filing cabinet where each drawer splits the remaining items roughly in half. Heap binary heap, a complete binary tree stored in an array. Insert push, theta of log n bubble up. Delete max or min pop, theta of log n bubble down. Find max or min, theta of 1. It models a priority queue like a hospital triage where the most urgent patient can be found instantly, but adding or removing patients requires reordering. Hash table separate chaining, array of buckets, each bucket a linked list. Average case search insert delete, theta of 1 if load factor alpha equals n over m is constant. Worst case all keys collide. Theta of n real world analogy, a set of lockers. If you know the locker number hashed, you can open it quickly, but if many people use the same locker, you must search through the pile inside. Graph two common representations. Adjacency matrix n by n Boolean or weight matrix. Checking edge existence theta of 1, enumerating neighbors theta of n adjacency list array of lists. Edge existence theta of degree of v on average, enumerating neighbors theta of degree of v for a sparse graph few edges adjacency list saves both space and time. Space complexity measures how much extra memory an algorithm needs besides the input itself. Total space, all memory allocated including the input-output and any auxiliary structures. Example storing a copy of an array of size n uses theta of n total space. Auxiliary extra space, memory used in addition to the input. Often we speak of in-place algorithms that require only big O of 1 or big O of log n auxiliary space. In-place criteria: an algorithm is in place if it transforms the input using a constant amount of extra storage, i.e. auxiliary space, equals big O of 1. Some textbooks relax the definition to big O of log n auxiliary, for example recursive quicksort. Quicksort, the partition step, rearranges elements within the original array, no extra array, big O of 1 auxiliary. The recursive calls add a call stack depth of big O of log n on average, so total auxiliary equals big O of log n. Mergeasort classic version allocates a temporary array of size n for merging, auxiliary theta of n. A careful bottom-up or in-place variant can reduce it, but the simple version is not in place. Dynamic array vector: when it grows, it allocates a new larger array and copies the old elements using theta of n auxiliary during the copy. But this cost is amortized over many insertions, see amortized analysis. Understanding the distinction helps when memory is a bottleneck, such as embedded systems, where only a few kilobytes are available. Amortized analysis looks at the average cost per operation over a sequence of operations, even if some individual operations are expensive. 3 common techniques: aggregate method, compute the total cost of n operations, then divide by n. Example, incrementing a binary counter. Flipping the least significant bit costs 1, every time it flips from 1 to 0 a carry propagates. Over 2 to the n increments, each bit flips exactly half as often as the bit to its right, yielding a total of less than or equal to 2n flips. Hence, average cost per increment less than or equal to 2 equals big O of 1. Accounting bankers method assign an amortized cost to each operation, storing surplus credits to pay for future expensive steps. Example, dynamic array vector with doubling strategy. Assume each push normally costs 1, but when the array is full we allocate a new array of size 2k and copy k elements, cost k charge each push 3 units, 1 unit for the actual insertion and 2 units saved as credit. The credits accumulated across the k pushes before a resize pay for the k copies, so amortized cost stays big O of 1. Potential method define a potential phi of d that maps the data structure state d to a non-negative number. The amortized cost of an operation equals actual cost plus delta phi. Example, splay tree. Define potential as the sum of logarithms of node depths. After a splay operation, the potential drops enough to offset the actual theta of log n rotations, giving an amortized big O of log n per access. These methods let us reason that, for many real-world structures, hash tables with resizing binary counters, union find with path compression, the average per operation cost is small, even though occasional operations can be costly. A lower bound shows that no algorithm can solve a problem faster than a certain rate in the worst case. 2 common ways to prove lower bounds. Decision tree model for comparison-based problems. For sorting and distinct items, each comparison yields a binary decision. The decision tree must have at least n factorial leaves, 1 for each permutation. Thus the height h is greater than or equal to log base 2 of n factorial, which is theta of n log, and therefore any comparison sort has a worst case big omega of n log n lower bound. Adversary argument, an imaginary opponent chooses inputs that force the algorithm to spend the most work. For searching in a sorted array binary search, an adversary can keep the target hidden until the algorithm has examined ceiling of log base 2 of n positions, proving a big omega of log n lower bound. Complexity classes categorize problems by the resources needed. P solvable in polynomial time, theta of n to the k for some constant k, on a deterministic Turing machine. NP solutions can be verified in polynomial time. NP complete hardest problems in NP. If any NP complete problem has a polynomial time algorithm, then P equals NP. Classic example, 3 SAT satisfiability of a Boolean formula where each clause has exactly 3 literals. The big omega notation used in lower bounds is the same as the big omega defined earlier. It gives a guaranteed minimum growth rate. Understanding lower bounds helps us know when it is worth looking for a faster algorithm. Often we cannot, and when we should instead aim for better constants or average case performance. Question 1, asymptotic notation. Show that f of n equals 3n squared plus 2n log n plus 7 is theta of n squared. Solution, for n greater than or equal to 1, 2n log n is less than or equal to 2n squared, since log n is less than or equal to n. Thus f of n is less than or equal to 3n squared plus 2n squared plus 7, which is less than or equal to 5n squared plus 7, which is less than or equal to 6n squared for n greater than or equal to 1. Also 3n squared is less than or equal to f of n. Hence choose C1 equals 3, C2 equals 6, N0 equals 1, therefore f of n equals theta of n squared. Question 2, best worst average case. A linear search looks for key k in an unsorted array of n distinct numbers. Assume each position is equally likely to contain k, and k may be absent with probability 1 over n plus 1. Compute the expected number of comparisons. Solution, let x be the number of comparisons. If k is at position I where I ranges from 1 to n, the cost is I probability is 1 over n plus 1 for each I, plus probability 1 over n plus 1 that k is absent, costing n comparisons. Hence expected x equals sum from I equals 1 to n of I over n plus 1 plus n over n plus 1 equals 1 over n plus 1 times open parenthesis n times open parenthesis. N plus 1 close parenthesis divided by 2 plus n close parenthesis equals n divided by 2 plus n over n plus 1, which is theta of n. Question 3, recurrence, master theorem. Solve t of n equals 4t of n over 2 plus n squared with t of 1 equals theta of 1. Solution, here equals 4, b equals 2, f of n equals n squared. C equals log base b of a, which is log base 2 of 4 equals 2. Since f of n is theta of n to the c, with k equals 0, we are in master case 2. Therefore, t of n is theta of n to the c times log n, which is theta of n squared log n. Question 4, amortized analysis dynamic array. A vector starts empty and doubles its capacity whenever it becomes full. Show that a sequence of n pushback operations costs O of n total time. Solution accounting method, charge each push 3 units. When a push does not cause a resize, 1 unit pays for the actual insertion, 2 units are stored as credit. When a resize occurs, suppose the array size before resize is k, we must copy k elements. Costing k at that moment, we have exactly k credits saved, 2 per previous push, but only half of those pushes contributed to this resize, enough to pay the copy cost. Hence, total amortized cost is less than or equal to 3n, which is O of n. Question 5, lower bound and p versus np. Prove that any comparison-based sorting algorithm requires omega of n log n comparisons in the worst case. Solution, a comparison sort can be represented by a binary decision tree, where each leaf corresponds to one possible permutation of the input. There are n factorial permutations, so the tree must have at least n factorial leaves. A binary tree of height h has at most 2 to the h leaves, therefore 2 to the h is greater than or equal to n factorial, implying h is greater than or equal to log base 2 of n factorial. Using Stirling's approximation, log base 2 of n factorial is theta of n log n. Hence, any such algorithm needs at least omega of n log n comparisons. Because sorting is in P, for example, merge sort runs in O of n log n, this lower bound shows the O of n log n bound is optimal for comparison models.